Okay, now I have another data set here. So you don't have to know where data set come from, but it used the same structure. It's not CSV anymore. Read equal, then df. Okay, so this is the original JSON responses from OpenAlex. So it has a DOI, title, display name, publication year, IDs, etc., and a lot of other columns here. I want to print the first one of the rows and see what is inside, right? The authorship column is what I'm looking for here. Do you see that? Okay, let's see what we got. Here are the authorship. First, it's a list. Everything will be a list. So what I need is I need the ID. I will construct the network using this ID, but not their names, because there can be duplicate names. The different person can use the same name. If I directly use name, they will be treated as the same person in the network, right? So I have to avoid that. So two things I need, but I still need who they are, right? I cannot tell who they are from this string, right? So what I need is, okay, I need to have the name too. So there are two things I need here. I need the ID, I need the name, right? So what I do, okay, I will extract author information from the authorship field. Yeah, Copilot is a time saver. Look at that. I even don't need to touch on anything. But whether it is correct, no, it doesn't seem to be right. Right. This is not something I need, actually. Yes, this is not something I need. So here we have a question here. We have a question here. So these are all the article. Each row is an article, right? And then there is an authorship column here. So we have a DOI. Each row is an article, and we have the authorships here, information here. How can we go from here and here? Difference. Dictionary. Change it into a dictionary. Yeah. There is a more efficient way to do this. There's a network we call bipartite network. Oh, okay. Bipartite network means it is more intuitive. Probably you say, okay, now you introduce another term. No, it's actually more intuitive. Draw this to you, you will know. The co-author relationship actually describes a relationship between the paper and authors, right? Let's see, these are the papers. And these are the authors. A1, A2, and A3, right? Make sense? Very intuitive. Here is another paper, P2. Let's call this P1. P2 is authored by A3 and also A4, right? This is more intuitive than the co-author relationship, I think, to you, right? Because they have the paper here, they have the author here. They have the paper here, they have the author here, right? So this is what we call bipartite graph. Bipartite graph. The author, why we call bipartite? Because there are two types of nodes here. This is the node one. This is one type of node, papers. These are another type of node we call authors, right? The authors. So the different type of nodes, they do not directly connect to each other. Like this P2 and P1, they never connected to each other because that makes sense if this is a co-author, if it is an author relationship, right? And A4 and A3, they do not directly connect to each other. They connect through paper, through this paper, right? This is called bipartite graph. Sometimes they call it affiliational graph because there's recording their affiliational relationship, right? So what we need to do is we need to convert this relationship to a unipartite graph. That is a co-author relationship. There's an algorithm automatically help you do this. You don't have to manually do that. So for this, what we will be doing is, let's say, here. Let's A1, A2, A3, let's say A4. What does the relationship look like? So 1, 2, 3, they have one co-author paper, right? So they will be interconnected. And A4 and A3, they have a co-author paper. So A3 and A4, they will be connected here. Yeah, let's do this. A4 here. So A4 and A3, they'll be connected here, right? So we are transcribing this network to this network, to this one. This is called the unipartite graph. Why we are doing this? Because in real life, this graph is more intuitive than this one, right? So what we are observing in the real world, most of the time, if they are affiliational, these are network like this. So first we need to construct this network, and then we construct this. You probably think, okay, I'm observing their co-author relationship. I can directly establish this relationship, right? So what you are doing, you are actually already converting it from this. Think about the data you are handling with, right? So you are already recreating their relationship according to this graph. If you think about that, right? So you already, when you have the data set for constructing this network graph, is because the data you have is already converted from this bipartite fashion. That makes sense, right? Now we have the issue here. How we have the task here. How we construct the network from this graph. This is very intuitive. One paper, a bunch of authors here. How can we do that? How can we do that? I don't know. Let's try. Totally improvised. Totally improvised. I can get stuck. I need bugs. I probably won't be able to finish them. See how it goes. Okay. Here's what I want to do. I want to have a data frame like this. So here is a DOI or OpenAlex ID, whatever it calls. This is 1, 2, 3. This is the data frame I'm going to construct. 1, 1, 2, 3. These are the authors. Author A1, A2, A1, A1. Make sense? So each line is a paper author. Make sense? So through this, I can establish a network like this. To make sense? Because each line is actually recording a connection in this graph. Are you seeing that? You see that? Make sense? Okay. For me, the task is very specific. Try to construct a data frame like this. So in many kind of data analysis work, what you are doing is first think about what is the structure of data frame you are going to use. That's a key here. That's very, very important here. Okay, that's my task. I will do it in a very explicit way, or you can say it is a stupid way to do that. So I will use a for loop to iterate all of those lines and construct this network. For, let me see, index in df is data frame dot index. Okay, authors. I think this line is something I need. Yes, but these authors, I'm not sure. I need another line. That is a DOI, right? Let's say I need the DOI, open Alex ID. Um, let's see what the original ID they're using. Open Alex ID. Okay, this is open Alex ID. I will use this item. It's so hard. I know. Open Alex ID equal to, thanks Copilot. Let's see it works. Yeah, it works. Okay, next. Authorships. What do authorship look like? The authorship look like this. What I really need is just the author ID and author names, right? So what I can do is I can use a for loop, use a list comprehension, S for S in authors. Uh, let's do this in a more intuitive way. Author, FIELD, author field for author field in this. It'll look exactly the same because I'm not doing anything right now. So next, what I want to do is, okay, author ID. So this should give me all the IDs of the authors, right? You see here, I have all the author ID here. Okay, next I want to add another field, which is the display names. Display name. Just that? I have the information I want. These are the unique ID and these are the names. This is what I need. I want to make it a data frame. Oh, okay, now I have the data frame. Okay, next, I want to add okay, I think there's enough work here. So let's make this a data frame. We call df authors temp because this is temporary, right? I will leave it here so you know what it is look like. But I will move it here. So let's see df temp, df author temp. No, I don't need this. df author temp look like this. It's not ideal. I still want to revise it. I still need to add something here. But let's see what are we going to do with it. Ah, no, this is not what I need. I'm going to. Yeah, I need to put the open Alex ID here. What I have here is the author here, right? This is just one column here, but I'm not separating them. For this one, I'm already separating them. So I have all the information about ID. I need the DOI. For this in case, I will the open Alex ID. What I can do is first simple open Alex ID equal to open Alex ID. Let's see what's the DF temp look like right now. What's wrong? Stopped. Kernel fail. Wait, let's just restart. It happens. Restart. Oh, it's so bad. It's just something wrong with the system. Okay, it started to work. So I have a data set here. Let's go through this and see how it will look like. Okay. Almost, very close, right? Do you see the data frame I'm having here? This 0 is OpenAlex ID, 1 is the name, and OpenAlex ID is here, right? So what this OpenAlex ID is here. So these are also ID. I want to rename them. df dot columns. So smart. Look at that. Yeah. Also ID, also name, OpenAlex ID. This is what exactly what I need. Okay, we got the issue here. We got a problem here. So why this is a problem? Sometimes it is possible there is no author name or no OpenAlex ID, some empty data frames, right? So I will rename it at the very end. So for now, I will leave it there. I will leave it there. Okay, now I need another data frame to have all them listed together, right? So this is just one paper. What I need is I need another data frame to put them all of them together. An empty data frame. Empty data frame here. Okay. And then I will put all this, I will concatenate them. df authors equal to pd concat the two data frames, ignore index true. Let's see what we have. Voila, we have it. We just need to rename it for the purpose of satisfaction. Columns equal to this. Okay. Yeah. Much beautiful. Also ID is here. Also name here. OpenAlex ID is here. Right? What are we going to do? We're going to construct network now. Import network X as an X.
Have a row for every author for in the word. So if the word has 9 authors, there will be 9 rows.
Yes.
Why don't you do it like column?
No, that's not a tidy data frame, right? And you cannot. So say the data frame here, right? So each observation is one connection. Each observation is one connection. Each observation is one connection here. Okay. So that's tidy data. That's tidy data. Now we have it. What we want to do is we want to construct network from this, right? Let's set a graph G bipartite equals to this. So this is a bipartite graph. Let me see if there is bipartite G graph. I'm not sure. Yeah, let's try that. I think it should work. Okay, this is a bipartite graph. We will say add nodes from, or let's do add edges from. Edges is links, right? From where? Like I said, each row is a connection, right? Is a connection, is an edge, What we're going to here is add the author ID and OpenAlex ID, right? Mm-hmm. But not author name. Why it is not author name? There might be a duplication. Yes. So I have to use this author ID and this OpenAlex ID. So we actually filling the author name. We actually replace the author ID with author name only after the replace the name. Yes. Okay. Yes, that's correct. I think that's a point where it is. Okay. df no, not this one. df author values. Look at that. So smart. Copilot. Yes, it's a copilot. You know you have to pay copilot, but if you have UT Austin the EDU mail, you can apply for free pro GitHub account. So with that GitHub account, you can also get a free kind of Copilot.
Okay.
Mm.
Oh,
I have the network. Now I have the network, bipartite network. Here. What I want to do is an X project graph. Projected graph. Yes, I think it is doing the right job. This is called projection. What I'm doing here is I'm projecting this graph to this graph, right? But I have to tell the program, what kind of nodes I want to return here. So here the nodes can be authors, can also be papers, right? But here I'm very interested in the authors here. So I tell the computer that, okay, these are the nodes I want to return. Please help me extract a network, unipartite network graph from this bipartite graph in which all those nodes are these authors. This is what this is doing. Okay. Done. G authors equal to this one. Okay, now I have the authors. Let's take a look. Nodes. I want to see the data equal to true. These are all the nodes here. They are all numbers. They are nothing here, right? I can also see ages. Age is data true. It give me ages. Okay, I believe there's just it's stuck here. It's just the too many ages, probably. So the computer stopped to respond. But here, this is very close to what I want, but I still need one additional thing. What?
Replace the ID with name.
Name. I need to know who they are, right? According to ID, I don't know who they are. So do you see the bracket here? This is actually where you will put the name there. Okay, next what? Yeah. Next, what we to do? What we're going to do is we will iterate all these nodes.
Oh, that's how it's built.
For node in nodes. It's so smart. I don't need to type anything. Look at that.
Correct, yeah.
Yeah, look at that. So G authors, but it goes too fast, right? It goes too fast. It's a time saver, right? But I actually used Copilot about a year ago, less than a year, about 6 months, less than a year. I feel it saved me a lot of time. Probably saved me on average every week if I do coding. If I use 10 hours with Copilot, I usually only about kind of 6 to 7 hours. It saved me about 2 or 3 hours every 10 hours, like that.
Did you buy it?
Like I said, you have a free version. If you use the EDU, use the UTexas, you can have free version about Copilot. You can get a free version, pro version of GitHub, and also a pro version of the free version of Copilot. Okay, back to this. Now, what do we do? It just goes too fast. Let's examine the code, right? The reason I know what I'm wanting is because timelessly, I work with the code. I was touched by the code. I know exactly I get frustrated. So I have the intuition. I know there's things there, but for you, things have to go slow, right? Go slow. Let's take a look. G authors node name. So I set an attribute to this node. So this node will be the node. Some of these numbers, this ID here, right? Tell the computer, okay, now I'm working with a specific node, and I will set this node a name. The name will be on the other end. I need to retrieve the name. Okay, the author ID equal to node, which is from here, right? The author ID. I'm searching on the right hand, on this hand. All these, what are these things are doing? They are searching a name to be set to the node, right? So that's what the other side is doing. So, okay, I have the ID here, the ID equal to the node name, and then the author name is the data frame, and then I have the values here. Let's take a look. Sometimes there'll be error, but that's very common. It's just a debug and see what the problem is there. Let's see the data again and see if this is something very close to what we want. Okay, look, there are names here. Do you see that? Now we have the node. This is a node. This is name. Are we stopping there? What we are going to do next? We still need. We need a what? Those network measures and node names. We have node names. Now we need network measures. We need to calculate the measures. Okay, let's go back. How we calculate calculate the node measures? It's very simple. Let's say we want to calculate degree centrality. Degree centrality of all these authors. Okay, it gives me the degree centrality of all the authors. This is a node, this is the degree centrality, right? What do we need next? We need to set these values to the nodes, right? We will go with very straightforward, very intuitive way and explicit way, but also very stupid way, but that's okay. It's for the showcase purpose. For node in author, let's guess. Let's guess if the Copilot know what I'm going to do. Yeah, it's very close, but not exactly what I'm going to do. See, I already give the suggestion that I want to calculate degree centrality here, but it gave me degree. That's okay. Let's keep the degree here. Can we do anything else? Let's enlighten the computer program with a few code. Ah, okay. It does. Look at that. You know, we are going to, or she know, we are going to calculate the centrality value here. We want to calculate more values. Can you think more? Give it a second. Okay, let's give it some clue. Okay, good. Closing centrality is good. Can you think more? The general centrality looks good. Let's take a look. Eigenvector centrality looks good too, although you probably don't know what it is. But let's have them all. Anything else? Okay, that's probably too much. That's probably enough. Let's stop here. Yeah, it takes some time. It takes some time to, especially for calculating the degree centrality. Okay, now you will see it will be very slow. Why?
There's so many nodes.
Every time for each node, it has to calculate all these values once, right? So do we have to do that? No, we don't have to. We can optimize this code by just calculating all these numbers once. Let's do this. So we have degree dict equal to probably okay. Degree centrality equal to good. Closest, good. Betweenness, yes. Eigenvector, great. Now we are going to do is we're going to revise the code here. Let's see if it know what we are going to do. No, we already have the dictionary here. Degree, give it a bit of suggestion. Degree centrality here. Yes, right. That's what we need. Here we already have the degree dictionary here. Let's revise this as well. Yeah, it know what we are going to do. Bless you. Between this, it knows we are going to do last one. Eigenvector. Okay, now it's already 2 minutes past. It's still working here, right? Because every time I have to calculate all the numbers. By doing this in this way, we only calculate all these numbers once, right? Then we will set these numbers to this. So every time here, it's just a retrieval, information retrieval, but not calculating all these measures again. So let's stop there and see if it is faster this time. You will still probably still take some time because those is eigenvector and between this centrality, they take some time. They have to iterate all those scenarios. For the degree centrality and degree, they are easy because it's just a count how many connections they have, right? Oh, right, we got results here. Let's take a look. Again, let's examine what the data look like. Now we have the node ID here. We have the attribute, the name attribute, the degree centrality value, colonial centrality value, betweenness centrality value, right? Look at that. We have all the information here. We have all the information here. What we need to do next is we need to save this graph and X2 graph right graph. Oh yeah, right graph ML. This is usually the things I use. G-authors the gram FML. Okay, now let's save the data. Let's check what it look like. This is a graph we just saved. Looks very similar, right? Very familiar to you. We just give you an example about this. There's the key, there's the data, there's a node, all these nodes here. See here, we are retaining six attributes of a node. D0 from D0 to D5. Do you see that? What are these attributes here? D4, D1, like this. These are attributes, detailed information about these attributes. Very straightforward, very intuitive. Next, what are we going to do? Yes, we are going to visualize it. Am I still recording the meeting somewhere? Ah, here. I will stop sharing the screen and I will share another. Gephi here. Okay. Okay, now we have it. Start Gephi. Okay, I want to open it. Make sure that we are okay with it. Let's share this so that it can be recorded. Hide. Next, let's open that file. Open the network. The network we just created is this one, right? Let's drag it. Nope. Okay, let's open it. Open desktop. Yeah, Gephi. Class. This one. Yes. So in this network, we have 5,000 nodes and 26,000 edges. It's pretty small. It's pretty tiny, right? I cannot make it larger. I apologize. I cannot make it larger. This interface is not easy to control. It's a mess. It's a mess. Yeah. But we can do some magic. All these there are nodes. We can do some magic. We can do on the modularity, which is a clustering algorithm. It will take some time because the clustering algorithm takes some time. It can also calculate the degree centrality, whatever we just calculated, we can use this interface to calculate as well. But the reason I'm not using it is because it is just too slow. This is a visualization tool, but this is not a calculation tool. So, okay, I have it now. Next, I want to show you different thing. I want to show different modularity class. I apply this. Ah, they have some color. Could I what? Yeah. No, hard. I cannot make it larger. For this interface, I cannot make it larger.
You're actually recording it.
I'm recording. Yeah, you can check the recording later as well. So next, I want to, do you see the layout here? Do you see the layout? This is all the layout, right? So this is the algorithm for controlling the layout. Do you still recall what I said? You cannot save the layout, but what you can do is you can control layout through this algorithm. These are the algorithm for layout. You can try different layout for sure. Let's try some of them. Some of the easy ones. It is moving. I will tell you, it is moving. But just because there are just too many nodes, it's moving super slow. Okay, what do we want to do? We want to refine. We want to make the network smaller. What we can do here, you see the attributes here. Filters, you see the filter here, right? The most commonly used are we call K-call, right? K-call. Let's see if we have K-call here. Ages, topology, K-call. I want to remove K equal to, let's do it. Not necessarily. Let me tell you why K is not necessarily degree. K-call is a way to expose core of the network. For this analysis, I just want to see the core of the network instead of anything else, right? Let's say using this network as an example. K equal to 1. It is stepwise. K equal to 1, it means, okay, first step, let's remove all the edges with only one connection. So for this network, I will remove this edge, and this edge, right? They only leave me with this 3 node. Looks like this core of the network, right? If I K-call equal to 2, then it will remove this as well, right?
So K is a step of the pruning.
Yeah.
How many steps do you prune?
Yeah. Yeah. How much depth? So it's more like a depth of pruning,
How many
right?
iterations?
Yeah. How many depths is in pruning? So if it is equal to 3, it will eliminate all those nodes. It is stepwise. First, it remove all the nodes with only one connection. And then you have a network, right? The next step, it will remove all the network with 2 connections, because if they have 1 connection, you already remove them, right?
Exactly.
But it is possible, if you remove 1 connection, there are possible some new kind of 1 connection nodes will emerge. It totally depends. So what I said, that's why I say it is kind of stepwise, right? Stepwise. So K-call equal to 3, we are using 5. So right now we have a smaller network. Let's see if it is moving faster. We have a huge core here, right? We have a core here. This is probably giant one paper. A lot of people are co-authoring. We can make it faster. Speed equal to 1, let's do 20. Let's stop there. So we see this topology here. We see the structure here a little bit, right? But it's not the end. We still need to do some, we want to make the importance node bigger, right? So we adjust the ring size here, ranking, choose a parameter. Let's choose a degree and see what it look like. Minimum size and maximum size. Maximum size let's do 20 and see what it look like. This mess here is like a mess. I don't like it, actually. So very much like a tumor or cancer or something. Usually, if you spot something like this, usually there are kind of a data issue. You need to check into this. Or sometimes there are these will be outliers. You need to check into them and see what the problem with it. This is not very good. Let's try another between centrality because they do not distinguish from each other quite well, right? So let's say this one. There are some nodes here. They became central, right? They became visible to you.
Actually work as a grade.
Yeah. So let's do this. I want to see the largest examples here. The large, these are the camps, this color, right? If they have the same color, it means that they belong to the same camp. So this is called clustering coefficient. Clustering here. Okay. Now I want to filter the graph attributes partition. Let's do the partition here. Partition modularity class. I want to show the first, second, and third. Okay, I will remove this. Select. Okay. Let's rerun this algorithm. Filter it. Rerun this algorithm. It look much better. It look much better, right? Yeah. But still, yeah, probably I use dark. It'll be better. Does it better? Look better? Okay. There are some of these nodes. I still want to see the difference. So max size, let's do 40. More apparent. Some of the nodes, they are here, right?
These nodes are authors, right?
They are authors, yes.
And so what would this tell these are like main authors in these works? Like
They are the structural hosts. Do you still remember the
Most
information?
connected.
They're connecting different parts, connecting different parts.
they're the bridge.
They are the bridges. They are brokers, yes.
Okay. And
So what I want to show you is, you see the between centrality, these are the nodes. They are important here, right? If I change it to degree centrality, still max size 40. It's not there anymore, right? The nodes are not there anymore. So this will give you a sense, depending on what kind of measures you use, the node, your result can be totally different. So what exactly measure you will be using, it totally depends on your research question. Am I right? Okay. Now, don't know how to enlarge this. Okay, you see something here, although not very clear on your end, probably. Next, we want to do the visualization part. Let's start getting it back to light. And then we turn on the label of these names. We want to see the label, these names, the author's names, right? But once we have it, we see all these kind of HTTP, they're the unique IDs. What are we going to do? These are the labels. We will not use this. We will use which one? Name.
Oh, it's already taking that? That's very good.
Yeah,
Name.
you stored it.
Yeah.
You see, you see all the names here, right? Do you see that?
Yeah.
It is up there.
How can I make it larger? So
Can you decrease the size of the
I want to have a mouse. Mouse I can use. Anyway. Okay, I want to make it larger, but given I'm not, I don't have the mouse with me, correct mouse with me, so I cannot make it. But want to adjust the node size according to I want to adjust the label size according to its node size. So once I click here, you see here, there are a lot of things, the details you have to really play with it by yourself. So I adjust the node size, adjust the size of the label according to the node size. Then you see some really big names here, right? Really big names here, which mean that these are instantly, these are the guys who are important in the network, right?
Or the betweenness centrality.
What did you say?
You did it on betweenness centrality, so they are important for the betweenness centrality.
Yeah, bridging the centrality, bridging the different knowledge camps. Yes, you are correct. Okay, now we have the network. Then I think we successfully get it done within a very short time. But as you probably can guess, there are just a lot of information here. I have it recorded, so you can replay it on your end.
So for the assignment, what would you want us to like have?
Produce a network like this and using different measures. Like this is betweenness centrality, right? And let's try the cloneness centrality. It doesn't tells you a lot of information here, right? So let's take a look at the degree centrality here. Not too much information either, right? So I think your observation is, depending on your research question, you need to choose an appropriate network measure to indicate, to measure your nodes and to present your results and draw a conclusion, right?